Down.
Sí.
Okay.
Del año.
Okay. So I think we should be good to go here.
Yeah.
We'll kind of pick up talking about instrumental variables. We should be able to kind of finish that pretty easily today. We'll be kind of picking up where we left off. We don't have a lot of slides to go through, but we'll kind of primarily be going back and forth between Stata and then kind of me drawing, kind of using the dot cam. So let's see here. Double check this that I'm not doing all this. It's still not working. Oh. So we left off down here, thinking about running these kind of two-stage least squares regressions. We said there's kind of a way that we can do this Stata that kind of does it all at once for us. And we were trying to identify kind of what makes good instruments. Kind of said there's two criteria. So that's where we left off. A couple of things I wanted to mention. Sorry, I'm very much derailed. I thought things were going to go, given that I have to use this. But a couple of things I wanted to mention before we get going. So the only thing left that's due in this class, we've got all the in-class quizzes done. All of the quizzes are essentially done. I said that last quiz, which is due by the end of the day tomorrow, right? That should just be a survey, right? So as long as you get that done, it should be an easy way to boost your grade in that quiz category, right? So make sure you're getting on and getting that done. Do it today, right? Get it out of the way. Don't worry about doing it even tomorrow. You could have been doing it after Tuesday's class. It's just survey-based questions, okay? So once that is passed, you'll be able to kind of see what your final quiz grade is. For the in-class quizzes, I now kind of have it set so that it's dropping your two lowest scores. So this is kind of like building in sick days. So it should now reflect, when you look on Canvas, your in-class quiz grade should only be taking your 10 highest quizzes. Okay? So that grade is kind of current up to date. The only other thing we will have is that kind of sixth and final problem set due at the end of next Tuesday. So we said a lot of that, you probably can pretty much already get it done. I think the only thing that we didn't cover on Tuesday was really the last question of that problem set. If we have a little bit extra time today, I might even open that problem set up and just give you a couple pointers, right? So that's the only other thing that we have to kind of do in the class, other than that quiz, which should be easy points. Any other logistical questions from me before we dive into material here today? Okay. So I mentioned also, just additional, I'll get an announcement up and we'll talk more about this next week, which we're just primarily doing review next Tuesday and Thursday. Our exam will be in this classroom, so we kind of lucked out. It'll be next Tuesday. I believe it's from 12:40 to 2:40. You can kind of check the syllabus with the time. It's got it in there. So where we left off, no, I've got to get way too many things open on my laptop because I wasn't expecting to do this necessarily. Up here. So we'll look at this IV do file class, okay? So we were down here. I added to this. So I've updated this on Canvas to kind of put some new stuff in that we didn't have on Tuesday's class. But we left off thinking about using this wage data set, this kind of free data set. So it's got all this information. We said if we run a naive regression, right, where we're trying to predict wages using someone's education. So if I do this, it's going to look like education increases my wages. Every year of education increases my wages by $72. I think these are something like hourly wages, so pretty significant, right? However, there might be things that we're not accounting for here that are causing omitted variable bias, right? So there could be things that are likely impacting both wage and education that we're not controlling for, which is going to cause a bias in our estimate. So we said one solution we have if we don't have the data is to use an instrument. The two conditions that we had, to be technical, were that we need it to be, first, we need it to be, we said kind of correlated, right? Z was kind of our instrument, correlated with the X variable that we're using, but we also needed it, and I said this is an easier way to think about it. I'll write out the more technical thing in a second. We need it to be uncorrelated with a Y variable. The actual kind of condition we need is that it's not with our y value, but it's actually that the instrument is uncorrelated with the error term in our regression, right? So once we've accounted for everything else, once we've used all of our other controls, once we've even included a control for that X variable that we thought had omitted variable bias, we need that instrument to be uncorrelated with anything else that those controls aren't accounting for. Okay. So we talked a lot about kind of how do we make sure this condition was met. So what did we look at from our regression to make sure that this condition was met? We said, what did we actually do? And we broke it down step by step. We can kind of use a shorthand. We run a first stage regression where we take the X value we want to use an instrument for. We run a regression using that instrument and then all other controls. Okay. We then use that regression to come up with predicted values for X. We then go to our second stage, which is our original Y variable that we were trying to understand the relationship between Y and X. And we'll use the predicted values of X and all of our other controls. What we won't include in this regression, you don't include the instrument in that second stage. All right? The instrument is only included in that first stage regression. Now, the other controls that you're using would be in both stages. Okay. Now, in Stata, we had an IV regress command that kind of did all this behind the scenes and then only gave us the second stage result. We then said at the end we could put comma first and it would show us those first stage results as well. So if we're looking at the first stage results, what are two pieces of information that we said tells us whether or not our first condition is met? Is the instrument correlated with X? Well, what's one thing that would tell us the relationship between X and the instrument? The coefficient on the instrument, right? So we said if that is statistically significant, that tells us that yes, there is some relationship between the instrument and X. They are correlated. Now, the other thing, we don't want to only rely on that because in our first stage regression, what could we also have? Maybe we're missing some controls that matter. Because our initial question was more about the relationship of Y and X, right? So it's a good piece of evidence, right, that our instrument is uncorrelated. But another piece of evidence would be this F statistic that comes from that first stage regression, which tells us is the amount of variation that we're explaining in our first stage from X, is it significantly different from zero? Now, F statistics, we didn't dive too deep into it, but when I've mentioned the F distribution before, remember we said there we actually have 2 degrees of freedom. So one of them is the number of observations. Before, when we were talking about other examples, it's usually like n minus k minus 1, or it's the number of right-hand side variables we've used. I'm not going to focus on that, what those degrees of freedom are. All we're going to be concerned about is from that first stage regression, a good general rule of thumb is if that F statistic is greater than 10, that's a good indicator, that's a pretty high level of statistical significance, no matter what those 2 degrees of freedom are, that we actually have an instrument that is correlated with our X variable. That when we included that instrument in our first stage regression, we were explaining a high level of the variation that existed in X, right? Or that it was correlated with the variation we saw in X. So these are our 2 pieces of information. We can rely on either one. Hopefully both of them point to the same thing. We'll have examples today where that's not always the case. Now, we didn't really focus on the second criteria that needs to be met. And I said that, technically, it's that we need the instrument to be uncorrelated with the error term of our regression. Okay? But if I ran a regression that looks something like this, where I include the actual X values, this was the variable I think had some omitted variable bias, and I thought I might need to use an instrument, and I also include the instrument. Well, then the interpretation of this coefficient is holding constant this value of X. Is the instrument correlated with Y? So what would actually be a good indicator that supports my second criteria? I need that correlation between Y and Z to be 0. So what do I actually want to do here? I want that coefficient to be 0. What do we start out assuming it is? 0. So I want to actually fail to reject the null, right? Because that second condition is that I need it to be uncorrelated. And all the other stuff we talked about, we're usually like, we want to know how is X impacting Y. Well, we still want to know that, but the condition we have is that Z needs to not be impacting Y. So there we could run a very simple regression like this. We wouldn't include all of our additional controls, simply the variable we're trying to instrument and the instrument itself. And then holding constant X, does the instrument have any correlation with Y? Hopefully not, because if it does, it's not going to be a good instrument. It would fail that kind of second criteria. Is that any questions on that idea? So we'll work through some examples, but this is kind of a summary of what we'll be kind of taking a look at. I'm just going to take a quick peek, wishful thinking. OneDrive's still not working. So we'll be going off my laptop, which is now falling asleep. It's not plugged in. So let's see if we can get this up. There we go. All right. So we had that naive regression. We think education has some omitted variable bias. What's something that we could use? I think I even introduced this idea last class. We've got father's education, right? That's likely going to impact the amount of education I get. So it'll be correlated with X. But should my father's education, other than its impact on my own, right? Remember, this is its correlation with anything in the error term for Y. Right? So it's anything that we haven't controlled for. Control for my own education. My father's education doesn't have any impact on my wage at all, right? Once I've controlled for the other things that it might have impacted, like my, I use the mouse, my own education. So here we could kind of run that first and second stage regression. My first stage would be, I try to predict my X variable using the instrument and my other controls. I then save the predictions for that X variable. So I called that education predict. I then run my second stage, which is the original thing I wanted to know, which is how does my own education impact my wages? But these predictions come from using my instrument. Okay. So this would be kind of my first and second stage result. If I run this regression here, I left this off for a second. So I'm going to copy and paste this here just to make this point. So if I were to run that same regression, but using the shortcut, which is IV regress, two-stage, least squares. And then I say, here's my X variable, here's my instrument. It'll do the exact same thing. It just won't tell me the first stage results, right? So if I actually run the first stage, save the predictions, run the second stage, I should hopefully get the exact same results as what IV regress shows me for that second stage. So we're going to hit enter here. I'm going to move this up here so it's easier for me to go back and forth. Sure enough, here was my first stage regression. Here's my second stage. And then that IV regress only gave me the second stage. Okay. Well, what's true about these results? I'm getting the exact same coefficients. I'm getting the exact, slightly different statistical significance here, which is, I'm guessing, did I forget something? Experience, age, married. Oh, so what did I do up here? So I did experience, age, married. I saved my predictions. Should be giving me the same number of observations. Oh, it didn't like a few of these. This is more further than I want to go into this class. I thought this wouldn't be true for this example, which is probably why I left the code out originally. So the statistical significance might be a little bit influenced here. If it's dropping some observations where there's no variation in X for the instrument. So even though it looks like it's using all the same number of observations, it's actually dropping a few of those. I can't see that behind the scenes, but it will give me that kind of same coefficient results. Okay. And that's really what we're focusing on. So if I gave you something on the final exam, I might ask you, what would the first stage regression look like? Just in terms of like writing it out, I would predict that X variable using my instrument. Second stage, I predict my Y variable using the predicted values of that X variable, but I don't include the instrument in that second stage. Okay. Now, I said that you could also write in here, I'm a first, And that will basically do the exact same thing, but will give you your first stage results as well. So here, what two pieces of information would suggest that this is either a good or a bad instrument, right? In terms of the first criteria. Well, what's my F statistic? First stage, it is 109, way above 10, right? Also, the statistical significance on my instrument is, I have a p-value of 0, highly statistically significant. So it meets my first kind of criteria to be a good instrument. And I said another way of checking to see, does it meet my second requirement? Okay? So, and I'll try to post this afterwards. So first criteria, F-stat of 109 is way greater than 10. I can type. And then statistical significance of the instrument, p-value is 0, so highly statistically significant. Right? So the next thing that we're going to want to take a look at is what about that second criteria? Okay. So the second criteria, I said one way we could check this is to simply regress my y variable on the x variable and the instrument itself. Okay. So if I run this regression, the coefficient on my instrument looks like here that it is what? Statistically significant. So that means I'm rejecting that that value is equal to 0. What did I actually want for my second criteria? I want it to be 0. So this would kind of fail that second criteria, right? This likely isn't a great instrument because it is correlated with the error term for my y variable of wage. So even though it meets the first, and I could ask you, these questions just because, it's not a good instrument, it still meets the first criteria very strongly. Doesn't quite meet my second criteria. It doesn't quite. It's not even close to meeting my second criteria, right? So these are kind of the two ways in which we could check to see whether or not those criteria are met. One thing that we also kind of talked,
Just to make sure, it's the second criteria is that we don't want X to be correlated with Y?
Nope. Right. So what was our second criteria? We don't want what are we trying to test? We're trying to see if this is a good instrument. So we want for that second criteria that the instrument that we're using is not correlated with Y. So the X variable we know is likely going to be correlated with Y because it has this omitted variable bias. Also, we think, the original setup was we thought education might impact wages. So we were expecting that to be correlated with. But what we don't want is any of that omitted variable bias, in our estimate for the relationship between X and Y. So we were trying to come up with an instrument that was correlated with X, but uncorrelated with Y. So we're looking at the instrument coefficient to see whether or not it's uncorrelated with Y. Is that?
Yeah. Thank you.
So here we don't have that being the case, right? It is correlated. We have a problem. Can't really use this as an instrument.
So the instrument isn't one of the other omitted variables, or it is one of the omitted variables?
It is an omitted variable, but if it's a good instrument, it would be an omitted variable that is not correlated with Y. Or I should say, said differently, technically it's that it's not correlated with the error term at Y. So this isn't like the most accurate way. If you were to go to the next level of econometrics, we have more sophisticated tests to do this. Based off of what we've talked about, this is where I'll kind of, as far as I'll push you, right? So because we know that a coefficient tells us whether or not two things are correlated, right? If we're looking to see if something is uncorrelated, we would want to be able to then be able to reject that. We want that coefficient to be equal to 0. So there's much more sophisticated tests, but we're not going to kind of dive into those. And this is as far as we'll kind of push checking that second criteria. Who's on that idea? Okay. All right. So we did some of this last class just to kind of prove this to ourselves. If I don't use any other controls, and this gets a little bit more complicated if I do include controls, so we're not going to go that far. But we said if I simply was using my X variable, if I use an instrument, if it is uncorrelated with that error term, the coefficient I should see should just simply be the ratio of the covariance of y with my instrument and the covariance of x with my instrument. Okay? So we can kind of prove this to ourselves. And this will be true whether or not it's a good or a bad instrument. So here I said, okay, if I run this regression where I'm using wage, X is my education, and the instrument is father's education, right? So I go ahead and I run this regression. I'll get a coefficient estimate of about 100.67. If I were then to kind of calculate the covariance between Y and my instrument and the covariance of X with my instrument, I can obtain those two values as well. So that's just 318, about 3.16. What should be true is that if I take the ratio of those two covariances, what value am I getting? Exactly what my instrumental variable coefficient is, which is 100.67. Now, this gets a little bit different if I add in additional controls. It gets a little bit more complicated. But as far as I would ask you, this would be, without controls, that coefficient I see from instrumental variable regression should be the ratio of the covariance of Y with the instrument over the covariance of X with the instrument. Any questions on that idea? And I think we looked at this in a different example. The next thing that we're going to want to do is kind of already jumped the gun. So I did that up here. So I had this in here. We were kind of testing that second criteria. So we already did that. I just kind of did that in a slightly different order, where we were regressing Y on X in our instrument, saying, can we reject, right? In our case, we rejected it, so it fails to meet that second criteria. I was trying to think of just other examples that maybe what would be good or bad instruments. So here's one where I looked at the first stage results, right? Instead of using father's education, I thought about using the number of siblings I have. So if a company hires me, will the number of siblings I have influence my wages at all? I mean, other than that it might impact other things. If I've controlled for the, if I think that the number of siblings is going to impact the number of years of education I get, then yes, it could impact it through that. But just on its own, directly, does a company care if I have 3 or 4 siblings when they're... Yeah. So should that instrument be correlated with Y? Wouldn't think so. So it's going to meet that second criteria. Now, the first criteria was, well, it still needs to be correlated with that variable of education, right? The thing that I thought I had omitted variable bias or measurement error, whatever I was trying to kind of eliminate. So siblings here, if I look at that first stage, right? Siblings impact on my years of education. Is it statistically significant? Yes. So it looks like one piece of evidence is it is correlated with the X variable I was trying to use it as an instrument for. And I think this kind of, the explanation in economics is that when a family has more siblings, how many resources are devoted to each kid? Or sorry, when a family has more kids, how many resources are devoted to each kid? Less, right? So are parents going to be more likely to be able to pay for college for all their kids if they have 5 instead of 1? No, so it's going to impact the number of years of education as I have more siblings. So it should be intuitively correlated with that X variable. And sure enough, we find that it's statistically significant. And what's true about the S statistic? Way greater than 10. So it meets that first criteria, okay? Now, does it meet the second criteria? Well, that's where I'm going to run a regression where I'm going back to, I wanted to initially understand the impact of education on wage. I knew that education was likely correlated with a lot of other things I don't have controls for, so I was trying to instrument for it using something else. So I chose the number of siblings, controlling for the years of education then. If siblings is uncorrelated with wages, it should kind of meet that second criteria, right? So I'll go ahead and run this regression. If I look at the number of siblings, p-value is 0, so that means I'm going to do what? Reject the null. The null is that coefficient is equal to 0. What do I want it to be equal to? 0. So it fails the second criteria.
What level are we going to use for that?
I mean, you could ask about any level, right? I could ask you at the 99, 95, 90% level, does it meet the second criteria? But right, if you said which levels would it kind of indicate that it doesn't meet the second criteria, we're still going to be comparing kind of those basic 3. Now, there's not a good general rule of thumb. So for this, like meeting this, if I saw, this is where like anything in practice to kind of capstone the class. If I was doing work for a company, what if I saw a p-value of 0.11? What would I be doing at the 90% level? Failing to reject. So there, I would have evidence that it is uncorrelated, but is it strong evidence? No, right? I mean, it just barely looks like it's not correlated, right? So, what's the actual cutoff we want? Kind of depends on what every researcher or company is actually comfortable with. Me personally, like we get really hung up on the 90, 95, 99% level. If you look at like academic work or you look at things that people are publishing out there, but just because it, if I fail to reject it at the 80% level, is that really that different than 9? I mean, a little bit, but not, it's still evidence, right? So there's not like a hard and fast cutoff, but this is what we would use. And I'll kind of keep it, I'll ask you questions, those kind of standard 3 levels, right? Now here it doesn't matter, right? Because we would reject that. So hopefully this kind of goes to show even some of these things that we think intuitively might be good instruments, it's really hard to meet these criteria sometimes, at least both at the same time. Okay. So I had another one, and where are we at with time? So I think this is interesting. If we have time, we'll come back to this. If not, maybe I'll save it for some review next class. But I thought this is an interesting example, given some things currently going on at this university. It's in a slightly different context. So here I get to use my device. So I posted this file. Oops. I posted it before class. It is, I had it up here. Maybe, I didn't add it. I put it under the files tab. So let me go here. There we go. So it's under the files tab. It should now show up on the homepage. It's this NCAA tournament data. So I had this thought once upon a time that maybe if I want to know, does the impact of applications to a university, I would think like IU, why do they want more applications? Because if I get more applications, if I'm admitting about the same number of students, what can I be? Here, I can admit higher quality students I believe will be of higher quality. So if I get more applications, what should happen to my incoming freshmen's average ACT and SAT score? To go up, right? However, the fact that IU is getting more applications is likely correlated with a lot of other factors that lead to why the student is applying there that would also lead to them being higher quality students. So I've likely got a lot of omitted variables that I'm worried about here. So I was trying to think, what would be a good instrument, right, for this? Because I know if I run the naive regression, so we can kind of think about this, not using instrumental variables, this is my naive regression. I'm looking at the average math SAT score of my incoming freshman class. I've controlled for the number of male, female undergraduates. I'll talk about the other variable in a second. I don't have a ton of controls here, but it looks like more applications does increase it a little bit. But maybe it's got a huge bias in it, right? Maybe actually getting more applications, like if they all look similar, maybe it actually won't have an impact on my incoming freshman's SAT, or maybe it's even larger than what I'm seeing here. I don't know. Now, my thought when I was coming up with this example was in March, when I sit down and look at NCAA tournament bracket, right? I see universities sometimes that I didn't even know existed, right? So if that's the case, maybe I am like, whoa, I didn't know that was somewhere I could pay in-state tuition there. Maybe I'll apply there, right? It's almost like free advertising. I just got done talking in my intro micro class. What does advertising do? It has 2 effects. It increases my cost, but it also increases potentially the share of market demand I'm getting. Here, this cost was, well, there was a cost I had to put into my athletic program, but it was kind of sheer luck that my team made it into the tournament. It's almost like I didn't change my athletic costs at all, but I've got this huge now, like almost like free advertising, and I might get a higher portion of demand. I'm going to be able to get more applications, right? So I'm going to control for whether or not that team was in the tournament the prior year, right? That should kind of be a good additional control. And then I'm going to think about the instrument that I want to use is what happened to the current applications following that year that I made the tournament. All right, so in that year I made the tournament, do I see more applications that year? So initially my thought was, well, this is top 64. That just means was I in the top 64 teams that made it into the NCAA tournament. So this was just basically a dummy variable. Did I make it into the NCAA tournament or not? What's something going on right now that might be very similar? Whether or not my university makes it into the
College football.
playoff. All right. So IU is probably loving this, right? They're getting a lot of headlines. They're getting a lot of news articles. It's essentially free advertising. So does it mean just intuitively, before we dive into the statistics, does it mean our first criteria? If I make it into the NCAA tournament and people that don't even like basketball are filling these things out, is it likely going to increase the number of applications I get?
Yeah.
Probably. But just because I make the tournament, does that mean that my students are inherently going to get smarter necessarily? Other than the fact that it might influence the number of applications I get and I can be pickier, I'm probably getting the same quality of applicants, right? When they go to the admission standards, they're still seeing the same kind of admission standards they were before. So I thought maybe it's uncorrelated with that Y variable. Right? So let's see if that's the case. So I'm going to run this instrumental variable regression. I'm going to kind of use the shortcut using the IV regress command, but I also want to see the first stage. Okay. So my first criteria, if I'm using basically a dummy variable for did I make it in the NCAA tournament or not as my instrument, is my first stage met? This is one that's kind of weird. And if you look at people who argue for instruments, the prioritized thing that we look at, we said we have two things we can look at. The F statistic, is it greater than 10? Barely, but it is. Right? Now, the second thing we said we would look at the statistical significance of the coefficient on the instrument. That's usually the second piece of information that they look at. Those two things don't always align. So a lot of people will just default to, is the F statistic greater than 10? In which case we would say we have a fine instrument here. Now, is it the best instrument? It's not very far from 10. So what ends up happening to the statistical significance of the coefficient on the instrument? P-value is a little bit lower than we would like to see, right? So does it meet the first criteria? Technically, using our general rule of thumb of the F statistic, yes. But that second piece of information is going to tell us like, yeah, you had an F statistic greater than 10, but this isn't the strongest instrument, right? Because its coefficient isn't statistically significant. We kind of go hand in hand with the fact that the F statistic, although greater than 10, pretty close to 10. In a general rule of thumb, as the F statistic gets higher, we would likely see this p-value get smaller. So this is a nice piece of information, or a nice example where we have one of the suggestions about our first criteria being met, but the other one not quite. And to your question earlier, well, we can't say it at the 90% level, but I don't know, I could say it at the 65% level. You know, that's not real strong, but it's greater than 50, right? It's greater than a 50-50 chance. So this is just a unique example where you would probably have to really convince people that this is a good instrument. And what could I potentially do to improve the F statistic or improve that statistical significance?
Drop either male or female undergraduates because there's.
I could drop my controls, but what's probably more advantageous to do is if I can make a statement without controls, is that weaker or stronger than being able to make the same statement with additional controls? I actually would want to have additional controls. Because if we think of going all the way back to like early stuff, if I just have, let's say I ran a regression where I said, as application goes up by 1, the average SAT score of my incoming freshman class goes up by whatever beta is. That's not near as strong of a statement as saying when applications go up by 1, the SAT of my incoming freshman class goes up by this, holding these 50 other things constant in my regression. So one way that we can usually increase that F statistic and decrease the p-value is by including more controls. Just like going back to when we were just simply looking at one control variable, well, it's going to include a lot of omitted variable bias. Or are we eliminating, as we add in more controls, a lot of that bias?
So there are a lot of multicollinearity with having both male and female undergraduates.
They would be correlated, but there wouldn't be perfect multicollinearity, right? If I look at, you can actually go pull the data. I mean, there's probably some schools, we could even look at it. Like kind of wild. Don't really know the explanation, but I mean, like This university has 1,000 more female undergraduates than male graduates, right? This one has about a little over 1,000 less, right? This one has, we want one, yeah, some have higher female, some have higher male, like it's all over the place. So even though they're going to be, or like they will be correlated, but there's not going to be issues of like perfect multicollinearity. Now, if I included total undergraduates, well, their total undergraduates is a direct function of male, and then I would have perfect multicollinearity concerns. That's why just breaking it down to those two groups, I don't. But if I included, say, total male and female, now I've got perfect multicollinearity concerns. Yep, you're thinking about this the correct way. So then that's the results from our first kind of condition. How would we test that second condition? Well, I'll include all of my controls. I'm also going to include my X variable and the instrument, right? So this would be like if I included the instrument in my regression, does it look like it's correlated with that Y value, right? So if I'm going to run this, here I look at, did I make it into the NCAA tournament? Does this meet my second criteria? So here's where we have to think about this a little bit harder. What is the second criteria? It's that the instrument is uncorrelated with Y. If I fail to reject the null that make me into the tournament is correlated with my Y variable, failing to reject is actually saying that that coefficient is equal to 0 or it's uncorrelated. So does this meet my second criteria? Yes, and rather strongly. P-value is 0.65. I'm nowhere close to being able to reject that null. So even though the first stage was kind of weak for that first condition, my second criteria is pretty strong. So there, I've got a pretty good instrument here, right? Or at least I would argue that it's pretty good, right? It's not the strongest for that first criteria, but it meets the threshold of an F statistic of being greater than 10. And the second condition is definitely looks like it's met. So that's kind of one way we can kind of test to see that. If you're interested, well, before I keep moving, any other questions just on this example before we keep pushing here a little more?
Would you say that it's more important then to look at the second condition rather than the first, or the second half?
So for the sake of like the questions I'll ask you, no one is any more important than the other. Right? I'm just going to ask you whether or not you have evidence that supports the first criteria, whether or not the evidence supports the second. Right? In practice, it's like anything else. In an ideal world, both of them would be strongly met, right? But if my first criteria is weakly met and my second criteria is strongly met, well, that's better than if they're both weakly met, right? So like, there's no like right answer there, right? Because I'm willing to give a little on one if the other one is strong, right? Trying to think of like outside of like a statistics, what this would be at, like, if you decide, if you're making the decision to use your time and you want to say, should I take my time to go work out? Right? I know when I work out, I don't, I feel I'm tired and I end up falling asleep earlier and I don't get as much work done. Well, there's a trade-off, right? Working out is good for my health, but it's bad because I don't have as much time to do other things, right? Well, I have to figure out for myself where what I want. It's the same idea here, right? Is it a good instrument? Should I be using it? Well, if the first criteria is really, really strong and the second is a little weaker, I'm okay with that. Like, it's always kind of a balancing act. But in an ideal world, and like to really convince other people that you have a good instrument, both of them should be strong, right? And we haven't really looked at an example yet, but really any of that's true. And that's really points to that when we're just going out and thinking about instruments, it's hard to find a really good instrument. It's hard to find something that has strong statistical support for both of those criteria. Okay. Does that answer your question? So just to be a little bit more precise, if you're just interested in like the next level or outside of this class, technically what I'm showing you here isn't really correct, because I said, for the sake of what we're doing, it's okay to think about that when we want our instrument to be uncorrelated with Y, okay, but technically that condition is that it's uncorrelated with the error term. So I can actually do that in Stata, right? I could run that regression, save my residuals, and then run a regression of my instrument on those residuals, right? That would actually be a better way of telling me whether or not the instrument is correlated with not Y, but with the error term, right? So that's what I did here. Now, usually this would kind of line up pretty similar to our other result. So notice here, the p-values are different. So when we didn't look at the error term, we had a p-value of what, 0.652. This is a nice example where what is its correlation with the error term? Well, that p-value is about 0.65. So I'd really be rejecting at very similar levels, right? But technically, if we were doing this, we wouldn't want to look at simply the correlation with Y, but we would actually want to look at the correlation with its error term. But for the sake of what I'm going to ask you, or what I would expect you to know, I mean, I would grade it, right? It's just that it's uncorrelated with that Y value. Okay. All right. I had some additional stuff here if we had time, but given where we're at, I want to do something a little bit different because I want to make sure we have time to get through this. Okay? So the last thing that we're going to talk about related to instruments is whether or not we should actually be using one. Okay? So up to this point, we've thought, I usually mention this as though we think there's some omitted variable bias that we want to control for using this instrument without having the actual data. This also, I said, could be simultaneous causality, measurement error. There's a bunch of different biases that instruments can solve. So to test whether or not we actually need an instrument, we have this Durbin-Wu-Hausman test, okay? So what we're gonna do is first, it looks like a first stage regression. I'm gonna regress my X variable on the instrument and all of my additional controls. So this really does look, it's my first stage regression. What I will do is save the errors from my first stage regression. So those errors should be any variation in X that I can't explain with my controls or with my instrument. If I then take those predicted errors from my first stage, so instead of using the predicted X values, I look at my predicted errors from that first stage. I then run my what looks like naive regression. So I don't use my predicted values of X, I use the actual values of X. So I'm back to running this naive regression where I haven't run the first stage. But instead of including predicted values of X, I include my predicted error term from that first stage. What this is doing is anything that's in that predicted error, a good way of thinking about it, it's any component of X, right, that the instrument can't explain. So when I run this regression, right, I assume that these errors from my first stage are exogenous or not correlated with my Y values. So I initially, my kind of null hypothesis is that the errors from my first stage are uncorrelated with those Y values, right? If they're uncorrelated, that would be that they are not related or that it is exogenous. So that's my null hypothesis, right? So if they're exogenous, this coefficient should be equal to 0. Right? So if I fail to reject, then that's good. That means those errors are not correlated with my Y. So here, if I reject, I'm actually saying that those errors are correlated with Y, or that there's a component of X that is endogenous to Y. So this was the idea that when I think about applications and the number of, average SAT score of a school, there might be things that are impacting both of those simultaneously, or that they're endogenous with each other, right? That they're somehow going to be correlated because of other things I haven't controlled for. So if I can reject the null on that predicted error term, that's telling me the null is that they were exogenous. That's telling me they are endogenous, and I actually need an instrument. Okay. So here we can kind of think about how would we do this in Stata, right? So I'll kind of scroll up here. Well, actually, we'll keep using the same example since we didn't the other one. So I'm going to go back up to this IV regress command. What do I actually want to do here? Well, one earlier. We'll do the beauty example because I think that'll be a little bit easier. We'll open that beauty data file back up. I come down here. We'll look at, who do I have the first and second stage? No, that I showed you this. Oh, it's right here. So we had kind of our first and second stage here. If I was going to run this Durbin-Wu-Hausman test, so what I would do, or remember originally our naive regression was just trying to predict wage using education and these additional controls. So I'm going to run my first stage regression where I've got my controls, I've got the instrument, and I've got that X variable. Then instead of predicting that X variable, I'm going to create a new variable, which is my predicted error term. Okay? And the command that I have for this, I believe it's just errors. Let me just see if I've got this. No, it's resid. So instead of predicting the X values, I'm going to predict the errors or the residuals, right? I will then take these predicted errors and I will include them. So now I'm just using the X variable. I'm also going to include these predicted errors in my original regression, right? So this isn't really my second stage now. I should probably call this, whoops, here just to kind of give you some comments if you're going back. We want to predict our residuals or error term from what looks like our first stage regression. Sorry, this laptop I'm not as quick with. We'll then kind of go back to trying to predict Y using the original X values for education, but also include these predicted errors. So if I do this, right? So it runs my first stage. It then saves the error terms. So this is now a new variable in my data set. Okay. I'm then going to kind of run that original regression, but include those predicted errors. So if I look at that regression, those predicted errors have a p-value of 0. Okay. So what is this telling me? Well, we originally started out, it helps, when we're running this Durbin-Wu-Hausman test, our null hypothesis is that that X variable is exogenous to Y. So another way of thinking about this is like the expected value of Y and X is 0, right? That there's no endogeneity. They're completely exogenous, right? And we know that's likely not going to be the case, but we say how strongly, and that's where we would look at that p-value of the predicted error term. So if I can reject the null for the coefficient on those predicted errors, what I'm saying is that there's some component of X that, my instrument removes that would be correlated with Y, right? So if I reject that null on my predicted errors, what I'm saying is I'm really rejecting that X variable was exogenous to Y. If I think that it is not, I'm rejecting it as exogenous, what I'm saying is that it's endogenous. I think that there's likely things I'm not controlling for that are impacting both. If that's the case, I have omitted variable bias, I need to be using an instrument. So this is a good example where what levels could I say I need to use an instrument? 90, 95, and 99%, right? I can strongly reject that these predicted errors are uncorrelated with that Y value. Okay. So this would be a test that we would use to argue for that we need to include an instrument. That the coefficient that we are seeing, if we simply run that naive regression up here, we didn't use an instrument or anything, those results are likely incorrect, right? But there's things we aren't accounting for, right? That would be endogenous to both wage and education. And we need to somehow remove those. How can we remove them? Using an instrument, right? So that's kind of one example that we have kind of for a test of, where did I go? I scrolled too far. There we go. The test to see whether or not we need an instrument. This would suggest we need to use one. Where are we at on time? All right. Let me think if there's anything else I want to say here, just given where we're at and given kind of the problem set. So I'm going to use this same data set. So I'm going to go back up here. I'm going to have third example now. I'm going to reopen the data just to get rid of anything else that I did before. Okay. So here's one where I have an example where I'm going to look at a slightly different example of an instrument, and we'll then kind of work through the criteria. We'll see, kind of test to see whether or not we need an instrument, all these same things that we've already, so nothing new, just a different example, right? So in this data set, there was IQ, right? So that seems like it might be a good predictor of wage, right? But there are likely things that are correlated with having higher IQs that also might be skills that are more valued in the workplace. So if I have a higher IQ, maybe I'm able to think through things a little more. I'm able to better time manage, which would also be rewarded in the workplace with higher wages, or I might have better kind of people managing skills, which I can't control for those things. So there's likely these like variables that I might have. Also, not even if there's an omitted variable bias, when I measure IQ, any test, SAT scores, ACT, IQ, they're not really the perfect measures of intellect, right? There's a lot of measurement error in those tests, right? And so one thing that you'll see a lot of people do is when we have these tests that try to look at someone's intellectual capability, we know that there's likely measurement error that exists in them. Well, if we have multiple tests of intellectual ability, we could instrument IQ with an additional test. So this had some information on this, I call it KWW. I don't even know what they use it for anymore. A lot of companies used to use it. It's called knowledge of the working world, right? It's kind of like a test that doesn't test so much your like mathematical skills, but more of like your people skills and how to navigate situations. So it would suggest the higher that your score is, like you're better at navigating the workplace, right? So it's likely going to be correlated with IQ, right? But this knowledge of the working world, it's not necessarily going to mean it's like knowledge and information that's like how you'd manage real life situations, but not necessarily that you're going to be any more productive of a worker. So I don't know if it's going to be a good instrument. I just thought maybe we could kind of take a look at it just to get a different example. Okay? So I initially might think this knowledge of the working world, it's a test that somehow measures ability, right? Now here's where even if it is a test of intellectual ability, when we use an instrument, the first criteria is that it has to be correlated with the X variable. So if this knowledge of the working world test and IQ are both measuring my intellectual capability, they're likely going to be correlated. They're both trying to measure my intellectual ability. But holding constant IQ, if I were to look at this other test, right, will it be able to explain, will it not be correlated with the Y value? Remember, what does it actually need to be correlated with? Anything else in the error term. So if I've already controlled for IQ, I've essentially already attempted to control for the person's intellectual ability. Should this second test be correlated at all with that Y variable? No. The only way that it's going to be correlated with my Y variable is any way that it's correlated with IQ, right? So it's not that it's uncorrelated with Y, it's uncorrelated with the error term. And because I've already used an additional, like another test that controlled for intellectual ability, this second intellectual ability test shouldn't have any relationship to that Y variable. That's the thought experiment, right? So what I can do is I can run the first and second stage regression, or I can just use that IV regress command. That's kind of my shorthand. So I might ask you to do both of these on the problem set. So here, what's the first stage? I look at that variable IQ, which I thought had measurement error. These tests aren't perfectly accurate. I'm going to instrument with with it, instrument for it with another test of intellectual ability, which is this knowledge of the working world test, and then include my additional controls. That's my first stage. I'm then going to predict those X values for IQ. So this is kind of the command that will do that for me. And then in my second stage, I'm going to try to predict wages, but using the predicted values of the variable I use an instrument for, which was IQ. Now, IV regress will do all of this behind the scenes for me, so it doesn't matter which I use, right? But I might ask you to actually code up and run the first and second stage result, not using the IV regress. I believe that's exactly one of the questions in the problem set. So this is what you would want to do. So if I'm looking here, I've run both these regressions. Here's my first stage, right? My X variable of IQ, my instrument of knowledge of the working world. So does this meet my first criteria? Does this knowledge of the working world test look like it's correlated with IQ? Well, the coefficient has a p-value of 0, so yes, pretty strong, right? It's 0. So we can definitely say that there's some correlation between IQ and this knowledge of the working world tests. Also, my F statistic is greater than 10. So here we have an instrument where both of those conditions that would support the first criteria being met suggest that it's being met. Now we have to kind of move on, right? Is that second condition met? So controlling for IQ, does this knowledge of the working world test, because remember, if I run this regression where I'm looking at wage being predicted by both IQ and knowledge of the working world, going way back to like stuff before the midterm exam, how would I interpret the coefficient on knowledge of the working world? For every 1 point scored higher on this test, the predicted hourly wage goes up by $12.6. What else do I have to add in? Holding all else constant, or holding the IQ of the individual constant. So because these are both tests of the same thing, I'm really already controlling for intellectual capability. What this second test does, it's almost like it's adjusting for the measurement error that existed in that IQ test. So here, when I run this regression, this isn't good, right? Because is that knowledge of the working world test, can I reject the null? The p-value is 0. Yes. What is the null? That the knowledge of the working world test is uncorrelated with wages. What is my second criteria? I need that variable to be uncorrelated with y. So it's not going to meet that second criteria here. So we've seen a lot of these examples where we think they're good instruments, but like it's really hard to meet these criteria in practice. But this is how you would look. This is the things that you would look at, or the statistics you would look at to kind of support that. Now, once again, what should I really be doing? I should be saving kind of predicted values and running the regression there. The final thing that we talked about, we're just doing another example here is, okay, even though this doesn't look like it's a good instrument, do I need to use some kind of an instrument here, right? So this was that Durbin-Wu-Hausman test. We said, if I run that first stage regression, and then instead of predicting my X variable, I save the error term from that regression. I save those residuals. If I then include those residuals in that original naive regression that I had, I start out assuming that IQ and wage are exogenous, right? That there's nothing that's influencing both of them simultaneously. I don't have omitted variable bias, or I don't have measurement errors. It's kind of, classical or even non-classical, right? So the null is that if this coefficient is equal to 0, that would tell me that these are exogenous. That was our null hypothesis. And that's essentially what we want. So if we can reject that, we're saying that it is endogenous and we actually need an instrument. So if I run this regression, first stage, predict the residuals, and then include the residuals in my original naive kind of regression, I look here, those predicted errors, I would reject the null. So remember the null here, you can almost think about the coefficient on the errors terms. It's synonymous with it. The null is that these X and Y variable, IQ and wage, are exogenous to each other. So if we're rejecting that, we're saying they're endogenous. There's things that are correlated with both that we haven't accounted for. We need to use an instrument. So here I can strongly reject that they're exogenous, or I found evidence they are endogenous, and I need to find a good instrument. Is knowledge of the working world a good one? Well, we said it meets the first criteria, but not the second. So we probably need to think of a second, some other instrument that's going to work here, right? But this would be evidence that we do need to think of another instrument to kind of account for this endogeneity.
The experience would satisfy that, right?
I mean, we could use experience as an instrument and test to see whether that's not the case. I don't know. I would think probably not, just intuitively. Because do you think experience is going to be correlated with wage? Probably. I mean, we could test it, right? So I could come down here and instead of using it as a control, I could try to use it as an instrument. My guess is, well, it meets the first criteria, looks like, but does it meet the second criteria? Here we would have to kind of run, oh. Well, it's better than the other one, right? I mean, I'm still rejecting the null, but at least I'm not rejecting it at the 99% level. So at least experience looks like it might actually be a better instrument, for that second criteria than even using, I forget what we were using before, that knowledge of the working world test, whatever it was. But still would not really meet, right? We would still be rejecting, so not quite. So we need to think of something else that would be a better instrument in this example. Yeah. Okay. Also, just one other thing to kind of point out here. So if I run this regression, instead of using that method where we actually test to see if it's endogenous, if I use this S-stat endogenous, it actually gives me a Durbin-Wu-Hausmann test, right? A result. So it's actually a much more complicated test than kind of how I've set it out to be for us. It's very similar the way it works. But this will kind of shorthand and do it all for us after you run that instrument. It'll pull the first stage, predict the residuals, put the residuals back in your naive regression, and then tell you whether or not kind of that Durbin-Wu-Hausmann test actually kind of meets a criteria. Now there, it actually accounts for that we have 2 degrees of freedom, which the method that I was kind of describing to you doesn't. I'm not going to push us this far, but just if you're kind of Googling things, you might see like this is another way to come up with that statistic. But we're not really focusing on the 2 different degrees of freedom from that F statistic. That's something that'll be a little bit outside of the context of this class. But that is kind of a little bit of a shorthand where you can see, does this do the Durbin-Wu-Hausmann test actually, can we reject that they're exogenous? Well, once again, here we've got kind of p-values of 0.46, so not quite. Now this like flips it, so it makes it a little bit easier. It kind of starts out assuming endogeneity, so we fail to reject it, so we need to include an instrument. So it still leads us to the same decision, right? But I won't kind of show you these types of results or expect you to know this. I'll kind of just expect you to kind of look at those results where we use those predicted errors, and then if we can reject the null on that predicted error coefficient, we're saying we need to use an instrument. So I guess it went a little bit more time than I thought today, just given me a little bit of time to kind of get things going. I'll clean this do file up a little bit, right? Based off what we did and kind of repost it, right? Just kind of make sure I don't have any typos based off what I was doing in class. Also include the edits that we made last class as well, just so it's a little bit better organized as you're kind of completing that problem set. But really anything you need to do, I mean, you're here, so let me just. Now I've got to remember where I have everything. It's going to be easier for me to do it here. So let's just do that. Let's go down here. I'll just want to point out a couple things so you don't lose easy points. So we're looking at that. It's problem set 6. So one thing I want to emphasize is when you're answering these questions, trying to give you some easy points when I'm asking you to like interpret coefficients. So one thing I would be careful on, the fixed effects portion. What did fixed effects do? It accounted for anything that was time invariant to what you're including fixed effects for. So your interpretation of every coefficient when you're using either first differences or fixed effects, excuse me, I believe in this example, we're looking at the effect of athletic revenues on applications, but we were including university fixed effects. So the interpretation would be athletic revenues, which I'm told up here are in millions of dollars. So what would the effect, how would I interpret beta 1? What's a 1 unit change in X? If athletic revenues are measured in millions of dollars, it would be 1 million additional dollars spent on my athletic, or sorry, brought in from my athletic program revenues would increase the number of applications by whatever this value is. But if I've included fixed effects, just like we talked before, it's holding everything else constant. What did the fixed effects hold constant? Anything that was time invariant to what I included fixed effects for. So what you would need to add into your interpretation here is holding constant anything that's time invariant specific to a university. So don't forget to add that into your interpretation. Right? This might seem like, why are we going back and doing these really simple interpretations? Well, that's not the main part of where the points are coming from. Where your main points are going to come from is the fact that you identify when I include fixed effects, it's holding constant anything that's time invariant of what you've included fixed effects for. And then down here, I would just say kind of making sure try to be as complete in your answers as possible, right? In this assignment, there is a little bit more explanation that's going to be needed to answer some of the problems as opposed to the code. And so being as explanatory as possible allows me to give more partial credit. So all of these, I'm asking, does it suggest it's a weak instrument or not? Make sure you're explaining why. Okay? So even, anything where you're asked, don't just say yes or no, give the reason why. Because even if you get the answer slightly incorrect, if you're still trying to compare the p-value to I'm going to be able to give you some points there, right? So even though some of these might seem like they're simple yes or no questions, right? You need to say kind of the reason why, right? So like, what to suggest it's weak or not. Well, the real suggestion would be because the p-value is less than not simply yes or no, right? Even like on this one, it's very easy to kind of forget, oh yeah, the null is that it is exogenous. So if I reject that, I'm saying it is endogenous. At least if you flip that, but you still tell me what, like I can still give you kind of half or partial credit for that. So make sure you're explaining as much as possible when it comes to this instrumental variable portion. Also, when you're doing some of these interpretations of the coefficient using fixed effects, don't forget to kind of add on, it's holding all else constant. But what is being held constant with fixed effects? Anything that is time invariant for what you included fixed effects for. Went a little bit past. Sorry, I was just trying to give you some things. I want you to make sure you're getting as many points possible on this last problem set. So I wanted to make sure I just mentioned a couple places where I see some easy points. Other than that, Tuesday, Thursday, what I'll start doing is fielding the class for questions on that practice exam or old quiz questions. Right? So you can go back and review those old quizzes, or you didn't have a quiz for this last stuff. You got practice problems. Those are all fair game as well. Any questions you have over practice problems, questions, or that practice final exam, we'll kind of work through those next week. Hopefully set us up pretty good for the class. But I would really encourage coming to class next week. We're going to see stuff that looks very similar to the questions I asked on the board. Okay?
For question 10, can we use that ESTAT test that you showed?
So I'll answer your question in a second. Let me start with